Hello. In the previous lecture, we developed a generalized long division in A bracket X for an arbitrary ring A. Generalizing the long division that we proved earlier in 100b, so where we showed that we can actually do the long division as long as the leading coefficient of the polynomial that we are dividing by is a unit, we generalized it for many polynomials g1 gn, and we said that if the leading coefficients of gi's generate the entire ring A, then we can actually divide f by these gi's in the following sense, that we can find some polynomial r with degree strictly less than the maximum of degree of g sub i's, so that f and r are representing the same coset modulo the ideal generated by g sub i's. In fact, we showed that we get the same result as long as the leading coefficients of all the elements in the ideal I are generated by the leading coefficients of g sub i's, and f belongs to the ideal I. Using the same principle, we showed that in order to generate an ideal I, it's enough to make sure that the leading coefficients of all the elements of the ideal I are generated by the leading coefficients of g sub i's. Using these results, we proved Hilbert's basis theorem, which says that if every ideal of the ring of coefficients A are finitely generated, then the same is true for the ring of polynomials with coefficients in A. So if A is Noetherian, then A bracket X is Noetherian. Using this, we show that every finitely generated F algebra or every finitely generated ring is Noetherian. Now, next, what we want to do is to study zeros of multivariable polynomials with coefficients in an algebraically closed field. Our general principle is similar to the Gauss-Jordan elimination process. Now, what do I mean by that? So I mean that it's going to be a kind of inductive process. Whenever I give you a system of equations with coefficients inside a field, we try to eliminate a variable x sub n, the last one, and then use that, use the smaller number of variables and repeat this process in order to solve the system of polynomial equations. But again, in this case, it's going to be very complicated. So as we've seen, even in the single variable case, it's going to be extremely complicated to understand zeros of polynomials. So we assume that if we reduce the problem to the single variable case, we can actually find the zero of the polynomial. That's one of the assumptions that we are going to make. The other one is that because we want to solve even the single variable cases, that means that we have to assume that the field is algebraically closed. Otherwise, there are many single variable polynomials that do not have any zero inside the field F. So these are the assumptions that we are making. Now, similar to the single variable case that we've seen, the tight connection between understanding zeros of polynomials and ideals of the ring of polynomials, the same is true in the multivariable setting. So we start with understanding or observing these type of connections in multivariable setting. Okay, so for a given family of polynomials, let's denote by z of s. So say s is a subset of a ring of polynomials. It might be finite or infinite. Let z of s be the solutions, be the common zeros of all the polynomials inside S. So if S is finitely many, so if there are only finitely many polynomials inside S, z of S is essentially solutions of a system of polynomial equations. So z of S is a subset of f to the n. It's the set of common zeros of the polynomial inside S. Now, similar to the single variable case, that instead of working with trying to find zeros of a polynomial, we switched it and went the other way around. We started with some alpha and then asked ourselves, what are the polynomials that vanish at this point? We can do the same here in multivariable setting. So essentially here, what we are doing, we are thinking about polynomials as functions. So viewing polynomials as functions, for a given subset V of f to the n, I can ask myself, what are the polynomials that vanish completely on the set V? What are the polynomials whose restriction to the set V is the same as the constant function 0? So again, that means what are the functions so that for every V inside the set capital V, f of V is 0. So that means the set capital V consists of the zeros of these polynomials. Okay, so now we have two types of functions. One of them takes a subset of polynomials and gives us a subset of f to the n. The other one does the other way around. Gets a subset of f to the n and gives us back a subset of ring of polynomials. Okay, now let's start with basic properties of these two functions, z and I. So the first thing is that if v1 and v2 are two subsets of f to the n, if v1 is a subset of v2, then the set of functions whose restriction to v2 is 0 is of course a subset of those functions whose restriction to v1 is 0. So as we can see, the first implication is rather easy, but it's an important implication. It tells us that I is inclusion reversing. The same is true for z. So if I tell you that S2 is a family of polynomials that contains S1, of course common zeros of S2 are going to be common zeros of S1 as well, because S1 is a subset of S2. So this means common zeros of S2 is a subset of common zeros of S1. So again, z is an inclusion reversing function. Now let's try to understand more structures. So now from set theoretic understanding of these functions, we want to go and try to understand the ring theoretic properties of I. Okay, so what is I of V? What can I say about this set? The first thing is that I of V is indeed an ideal of the ring of polynomials. One way of seeing this is by saying that, as I indicated, I of V is essentially about those functions those polynomials whose restrictions to V gives us the 0 function. This means I'm taking every polynomial, so let me erase this and rewrite it. So this means that I'm taking a polynomial, view it as a function on f to the n, and then restrict it to f. So that way I get a function from V to f. And because of the way that we have defined addition and multiplication of polynomials, essentially they are pointwise addition and multiplications, we do know that this viewing polynomials as a function and then restricting to V is indeed a ring homomorphism. And the way that we are defining I of V is precisely kernel of this function. So again, the function is, I give you a polynomial, you just think about it as a function and restrict it to V, and then the kernel of this map is I of V. So clearly, it's an ideal of the ring of polynomials. Now, moreover, if you think about it, V is definitely a subset of the common zeros of I of V. Why is that the case? Because I of V, by definition, consists of polynomials whose restriction to V is 0. That means V is a subset of zeros of all the polynomials inside I of V. V is a subset of all the common zeros of functions or polynomials inside I of V. That means V is a subset of Z of I of V. The third property is that for every subset of ring of polynomials S, the ideal generated by S is a subset of I of Z of S. Why is it the case? The reason is rather simple. So what does Z of S mean? Z of S means common zeros of S. Now, what does I of Z of S means? It means what are the polynomials whose restriction to Z of S is 0? Of course, every element of S has this property, because Z of S by definition consists of common zeros of elements of S. So S is a subset of I of Z of S. But by the second property we are going to show, and we have already discussed, that I of Z of S is an ideal of the ring of polynomials. Since S is a subset of this ideal, the ideal generated by S is a subset of this ideal. So that implies part 3. And now in part 4, we argue that zeros of a set S is the same as zeros of the ideal generated by S. Because of this, we don't see any distinction between understanding zeros of a family of polynomials or zeros of the ideal generated by the family of polynomials. So we will be focusing on understanding zeros of ideals, common zeros of elements of an ideal. And finally, we finish this lemma by showing that common zeros of a family of polynomials can always be captured by only finitely many of those polynomials. We don't need to work with infinitely many equations. If you give me infinitely many equations, I can always find only finitely many of them that give me the same set of zeros. Okay, so this is the hardest part of this lemma, and essentially we will be using Hilbert's basis theorem in order to show the last part of this lemma. We have already proved many parts of this lemma, but let me go through the arguments again, but rather quickly. So let's start with part 1 again. So knowing that F belongs to I of S sub 2, that means restriction of F to the set S sub 2 is 0. Set S sub 1 by assumption is a subset of S sub 2. That means restriction of F to S sub 1 is also 0. That implies that I of S sub 2 is a subset of I of S sub 1. Now, similarly, if I tell you that I sub 1 is a subset of I sub 2, and I pick a common zero of all the elements of I sub 2, because I sub 1 is a subset of I sub 2, clearly that element V is also a common zero of all the elements of I sub 2, which means V belongs to common zeros of I sub 1, and we get the implication. We get that the common zeros of I sub 2 is definitely a subset of common zeros of I sub 1. Now, the reason that V is a subset of Z of I of V, we have already discussed. Let me give an alternative argument on why I of V is an ideal of the ring of polynomials. In order to show a subset is an ideal, I need to show that it is not empty, and at the same time, if F1 and F2 are in this set, then for any other polynomial, F times F1 plus F2 is also inside this set. So why is it not empty? It's because the constant polynomial 0 is there. Now, let's see why we have the property that F times F1 plus F2 is also inside this set, assuming that F1 and F2 are in this set. Knowing that F1 and F2 are in this set means that restriction of Fi's to the set V is the constant function 0. Now, when I look at f times f1 plus f2 and evaluate it at some element, small v, then because f1 of v and f2 of v both of them are 0, we deduce that the value of this function is also 0. And that implies the claim. Now, as we have mentioned it earlier, for every f inside the set S and every v inside the common zeros of S, we have that f of v is 0. That's definition. That means when I restrict f to the common zeros of S, I get 0 for every f inside S. That means what? That means f belongs to those polynomials that vanish at the set restricted to the set Z of S. That is true for every element of the set S. So S is a subset of this I of Z of S. Because I of Z of S is an ideal that we have proved in the previous step, in the previous item, because this is an ideal and S is a subset of this, we deduce that the ideal generated by S is a subset of this. So that gives us part 3. Now, to see part 4, let's again see, using part 3, we know that the ideal generated by S is a subset of I of Z of S. What does that mean? It means for every element of this, for all F inside the ideal generated by S, and every V inside the set Z of S, when I restrict F to this set, I get 0. That means what? That means every vector here is a common 0 of all the elements of the ideal generated by S. Every element here is an element here. On the other hand, S is a subset of the ideal generated by S, of course. And Z is an inclusion reversing function. That means Z of the ideal generated by S is a subset of Z of S. Now I have both sides of inclusion. That means that equality should hold. Now that I know the common zeros of a set is the same as the common zeros of the ideal generated by S, by that set, I can use Hilbert spaces theorem. By Hilbert spaces theorem, we know every ideal of the ring of polynomials with finitely many variables is finitely generated, because that's a Noetherian ring. That means the ideal generated by S is a finitely generated ideal. So I can find some GIs inside the ring of polynomials, in fact, the ideal generated by S, so that I end up getting the same ideal. Now, the set of zeros of S is the same as the set of zeros of the ideal generated by S. That ideal is the same as the ideal generated by G sub i's, and the set of zeros of ideal generated by G sub i's is the same as the set of zeros of G sub i's. So that means I can choose only finitely many elements to get the same set of zeros. Now, let's go back to the original question. We want to understand zeros of a system of binomial equations. We will be much more humble, and we want to understand if we can find only one common zero for these G sub i's under suitable assumption. So that's our goal. We want to show that under suitable assumptions, we can find a zero, a common zero for a system of polynomial equations. And our general approach is inspired by the elimination process. But what does that mean? When I say elimination process, that means we want to roughly eliminate variable x sub n. And that means what? We want to derive equations from the equations that we are given, so that these new equations that we get do not have xn's in themselves. So that's part of eliminating x sub n. And moreover, we have to be able to find x sub n in terms of the previous variables. So if I give you previous variables, then we should be able to find what x sub n is. So there are two parts in an elimination process. So the first thing is finding certain equations for the previous variables, x1 dot x sub n minus 1. And the second one is finding or solving for x sub n for given x sub i's. Okay, so this one, the second item is a bit more vague, but let's see what I mean by that. Now, let's think about this. The way that we can derive equations from a star is essentially by looking at multiples of g sub i's, adding them, and so on. That means we are essentially working within the ideal generated by g sub i's. And when we want to eliminate x sub n, if we want to arrive to a polynomial that where x sub n does not appear, that means we are essentially considering the ideal generated by g sub i's intersected with the ring of polynomials with variables x1 dot x sub n minus 1. So essentially, we want to work with this ideal and try to understand zeros of these polynomials, this system of equations. Now, suppose that you have already found a zero of this polynomial that has less number variables. Now, for given a sub i's, we want to find x sub n minus 1. We want to find a solution for x sub n minus 1, for x sub n equals to a sub n, so that these equations that we have are satisfied. So essentially, we plug in a sub 1 dot a sub n minus 1 for x sub i's, and then we get single variable polynomial equations, and we want to solve them and find out what x sub n is. What is not clear is whether or not this system of polynomial equations have a zero. Maybe we get unlucky and those polynomials do not have a common zero inside F. Now, what we want to do is to find out precisely under what conditions such a system of equations have a common zero. Now, let's try to formalize what we have been doing. Essentially, we looked at the set of zeros of I, and then we projected that. We forget about the last component and project it only to the first n minus 1 components, and definitely whatever we end up getting is a common zero of polynomials that are inside I but do not have x sub n in them. Because I started with zeros of I, definitely those elements are zeros of this. So when I project them to the first n minus 1 entries, then I will go from z of I to the z of I intersected with f bracket x1 dot x sub n minus 1. Now, next, what we want to do is to take some element in the fiber, in the preimage of a1 dot a sub n minus 1. We want to find a sub n so that the first n minus 1 components are already given to us. But it's not clear at all why we should be able to do it. In fact, in general, it is not true that this pi is surjective. It's not hard to come up with, it's not hard for us to come up with an example where pi is not surjective. So in general, it's not true that pi is surjective. So I leave it to you to come up with an example where this is not surjective. It's not hard. Now what if it's not surjective? Then how can I proceed with this argument? So what we will do is to replace the standard n minus 1 dimensional subspace with some other n minus 1 dimensional subspace. We will choose it in a careful way so that this pi is surjective. So what we will do, we start with a situation where pi is not surjective, and pinpoint exactly what happens when this is not surjective, and then try to avoid it by replacing the standard n-1 dimensional subspace by some other choice, by some other n-1 dimensional subspace where that problem doesn't arise. So that's our method of proving, of finding some element inside Z of I under the right condition. So again, our technique is to find out under what condition pi is not going to be surjective, and then try to avoid it by showing that we can indeed find a right n-1 dimensional subspace where this projection ends up being surjective. Okay, so that's our general method. Let's go to the details of the argument. So our standing assumption at the moment is that this pi is not surjective. That means we have managed to find a common zero of I intersected with ring of binomials with one less variable. But this element is not inside the image. That means that this projection is empty. The preimage at this point is empty, which means there is no common zero of the ring of the ideal I, and with the first n-1 components being a1 dot a sub n-1. So again, this preimage means all the n tuples where the first n tuple are the same as the one that we are given, and this n tuple is supposed to be a common zero of all the elements of the ideal I. Now, by the assumption this set is empty, but what does that mean? Let's try to understand this. So again, if I think about it, this is supposed to be 0. This means that the first n-1 entries are fixed. This means essentially I'm evaluating my polynomials inside I. I'm substituting a sub 1, a sub 2, a sub n-1 for the first n-1 variables. And then I'm asking myself if I can find a sub n for the last variable so that all these equations vanish. So this means I'm using this evaluation map at the vector a1 a sub n-1 from the ring of polynomials with n variables, evaluating the first n-1 of them, and end up getting a polynomial only with variable x sub n. So essentially, I give you a polynomial in n variables, evaluate, substitute a sub 1 a sub n-1 for the first n-1 variables, end up getting a polynomial with variable x sub n. And I apply this ring homomorphism to all the elements of I, and I ask myself whether or not these single variable polynomials have a common zero. If they do have a common zero, that would be a solution for us for x sub n. That means a sub 1 a sub n is a common zero of I. Under the assumption that this set is empty, we deduce that these single variable polynomials do not have common zeros in F. Okay, so that's our assumption. But remember, single variable polynomials with coefficients inside a field is a PID. Therefore, this ideal is a principal ideal. Of course, the generator depends on the vector A that we have chosen, but it is definitely some principal ideal. Now, whether or not this principal ideal has a common zero just depends on the generator. If the generator has a zero, then the every element inside this ideal has a zero, and it's the same as the one that the generator has. So everything boils down to understanding whether or not the generator has a zero. Now, generator is a polynomial. If I assume, and I will from this point on, if I assume that my field is algebraically closed, then every non-constant polynomial has a zero. So if I tell you that this ideal does not have a zero, does not have a common zero inside this algebraically closed field F, that means this generator cannot be a non-constant polynomial. At the same time, if it's the zero polynomial, we are done. So this polynomial should be a non-constant, non-zero polynomial. That means a unit. That means this ideal is the entire ring of polynomials F bracket x sub n. That means 1 belongs to this ideal. So again, let's emphasize this. So knowing that this is empty is equivalent to saying that the generator is a unit, and that means this assumption that for some a is not inside the image of pi, this assumption holds precisely when one belongs to the image of I under the evaluation map, evaluating the first n minus 1 variables, substituting a sub i's for x sub i's for the first n minus 1 variables. Okay, so in order to understand this better, we are going to view our polynomials as polynomials in terms of x sub n with coefficients inside the ring of polynomials with variables with indices less than n. And because we are going to assume a star holds, that means we are going to assume that 1 belongs to this, which means we are going to assume that for some f inside the ideal I, when I substitute a for the first n minus 1 variables of f, I end up getting the constant polynomial 1. Now, in order to understand how this evaluation works, I'm going to write down f in terms of a polynomial with variable x sub n. That means I'm going to consider these coefficients. These are essentially polynomials in n minus 1 variables from x1 till x sub n minus 1. So f is a polynomial in terms of x1 dot x sub n minus 1 times x sub n raised to power d. The same for x sub n raised to power d minus 1, and so on. F sub 1 x times x sub n plus f sub 0, and it is inside the ideal I. And f sub i's are in the ring of polynomials with one less variable. So from this point on, I'm going to denote the ring of polynomials with one less variable by the letter capital A. At some point, I might relax this condition for letter A and even assume that it's a unital commutative ring. But for the purposes of proving the result about the ring of polynomials, A is always the ring of polynomials with variables x1, x sub n minus 1. Okay, so now when I evaluate f at A, I end up getting the constant polynomial 1. What happened? So when we say that when evaluated, I get the constant polynomial 1, so this A is substitute is plugged into all the coefficients. These coefficients are polynomials that depend on the variables x1 dot x sub n minus 1. So we are essentially evaluating these fi's at A. We end up getting a polynomial in terms of x sub n. Now, knowing that this polynomial is supposed to be the constant polynomial 1, we get this equality. The constant polynomial 1 is supposed to be f sub d evaluated at A times x sub n raised to power d plus f sub d minus 1 evaluated at a times x sub n to power d minus 1 dot 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 f sub 1 evaluated at a times x sub n plus f sub 0 evaluated at a. Now, these two polynomials are supposed to be the same in the ring of polynomials with coefficients inside f. That means coefficients should be equal. Here, the only coefficient is the constant term. That means all the other coefficients over here should be 0 except the constant term. So f sub d evaluated at a, f sub d minus 1 evaluated at a, f sub 1 evaluated at a, all of them are 0. And f sub 0, the constant term evaluated at a, is 1. I forgot to write it down. So we end up getting this system of equations. Now, what we want to do is to get more equations with no variable x sub n. That means we want to get more elements inside A and inside I. Now, suppose I give you some element inside I. That means every linear combination, or linear combination meaning with R and S inside the ring of polynomials. So any such polynomial is already inside I as well, because G is assumed to be inside I and F is already inside I. Therefore, RF plus SG for every R and S that are polynomials in n variables are already inside I. Now, our question, we want to find such things inside A, where there is no x sub n. So that's our goal. We are looking for elements of this form that are inside A. So now we can simplify our notation a bit and formulate this question. Let's say I give you a unital commutative ring, capital A, and I give you two polynomials, two non-constant polynomials inside this ring. How can we find elements inside the ideal generated by f and g that are in the ring capital A? Can we come up with a mechanism to find such an element? So that's a general question that we want to address, but let's see how we are going to use it. The point is that if I find such an element, then we know this A that we have, the assumption was that this A was a common 0 of all the elements that are inside I and do not have x sub n as a variable. So if we find such a linear combination inside I intersection with A, it's already inside I. If I find it inside A, then it will be in the intersection. That means that if I evaluate this polynomial at A, I should end up getting 0. This is the main resource of ours. So we are going to use this. So our information is all about the element A. We know that this is a common 0 of this ideal. So I need to produce more elements inside this in order to be able to use the assumption that we have. And this is how we are going to do it. Okay, now let's go to this question. I give you a unital commutative ring, capital A. Can we have a mechanism to find an element inside the ideal generated by f and g and the constant polynomials? Okay. The easy case is when A is a field. So let's go back there and get inspired, and then we come back to the general setting later. When A is a field, we know that the ideal generated by f and g is the same as the GCD of these two polynomials. So this intersection is non-zero precisely when f and g are co-prime. If they are not co-prime, then there is no non-zero, non-constant And there is no non-zero constant element inside the ideal generated by f and g. We know that using Euclid's algorithm, we can find R and S so that the GCD is RF plus SG. Now, the question is, can we be economical, and can we find small degree R and S with these properties? We will show that, in fact, we can find polynomials R and S so that degree of R is at most degree of G is strictly less than degree of G, and degree of S is strictly less than degree of F, so that their summation is the GCD of F and G. So this is what we are going to show, that degree of R is at most degree of G, and degree of S is at most degree of F. So this is, so RF and SG, both of them are going to have degrees strictly less than sum of the degrees of F and G. Okay, so that's our claim. So essentially, we are claiming that we don't need to consider large degree polynomials. I can focus only on those polynomials whose degree is strictly less than degree of G and strictly less than degree of F. Okay, let's see how the proof goes. We know that f bracket x is a PID, and therefore we do know GCD can be written as some polynomial times f plus another polynomial times g. Now I want to find smaller degree polynomials. The inequalities that are given are already suggestive. We have to divide r tilde by g and s tilde by f. So let's do that. Using long division, we end up writing r tilde as a multiple of g plus remainder. And being the remainder means degree of r is strictly less than degree of g. It is in the range that we are interested in. Similarly, s tilde can be written as a multiple of f plus a remainder, and remainder means that degree of s is in the range that we are interested in. Now, I'm going to use these equations, this one and these ones, and replace r tilde by this, and replace s tilde by q sub 2 times f plus s. We end up getting the GCD of f and g is, instead of r tilde, I write this times f, plus instead of s tilde, I write this times g. Distribute and reorder the terms. We get f times g from here and f times g from here. Factor it out. I get f times g times q1 plus q2, adding up the quotients, plus r times f plus s times g. Now, let's take this on one side and bring these guys to the other side. So gf times q1 plus q2 is GCD of f and g minus rf minus sg. Now, let's compare degrees. Degree of this side is sum of degrees. It's degree of g plus degree of f plus degree of summation of qi's. How about the other side? Hey, I'm adding these polynomials. So the degree would be at maximum of these degrees. Degree of this one. Degree of GCD cannot be more than the minimum of the degrees. Okay, so it is at most, let's say, degree of f. Now, this one is at most degree of, it is degree of f plus degree of r, but degree of r is strictly less than degree of g. So it is at most degree of f plus degree of g minus 1. The same is true for this one, because degree of s is strictly less than degree of f. So this means that all the terms, this one, and this one, all of them are less than or equal to degree of f plus degree of g minus 1. Now, I can cancel out these two some terms, end up getting the degree of q1 plus q2 should be a negative number. But that's not possible unless this is the zero polynomial. That means Q1 plus Q2 should be 0. Now that that's 0, this disappears. We end up getting that GCD is R times F plus S times G, and R and S are the degree of R and degree of S are in the range that we are interested in. Degree of R is strictly less than degree of G, and degree of S is strictly less than degree of F, and that's exactly the lemma that we claim. Okay, so now when A is a field, we understand that it's enough to focus on this range of binomials. It's enough to focus on the pair R and S, where degree of R is strictly less than degree of G, and degree of S is strictly less than degree of F. Now, this inspires us to consider the same for an arbitrary unital commutative ring, capital A. Let P sub I be the set of the ring of polynomials with degree at most I. And let's consider the following map. So again, P sub I is the set of all the polynomials that have degree at most I. And we are interested in R times F plus S times G, but I'm going to focus only on those pairs of R and S's, so that R has degree at most M minus 1. M is degree of G. So R is the one that's multiplied by F. Degree of this guy should be at most degree of G minus 1. And degree of this one should be strictly less than degree of F, which means degree of it is at most degree of F minus 1. So let M be degree of G and D be degree of F. Then R has degree at most M minus 1 and S has degree at most D minus 1. So I'm going from P sub M minus 1 cross P sub D minus 1 to, now, when I do this computation, RF has degree at most D plus M minus 1. SG has degree at most D plus M minus 1. When I add them, I get a polynomial whose degree is at most D plus M minus 1. And notice that this polynomial, every element is can be uniquely written as this: a sub 0 times 1 plus a sub 1 times x plus a sub 2 times x squared plus a sub I times x to power I. So in some sense, I can say that this has so if A was a field, I could have said that this is a vector space of dimension I plus 1. So this one is of dimension m, this one is of dimension d, and this one is of dimension d plus m. So this means these things should have the same dimension. Now here, I don't work with a field. I'm working with an arbitrary unital commutative ring, but nevertheless, I can use these concepts and represent this map, which is an A-module homomorphism. I can represent it using a matrix. Again, because every element here is a linear combination of x to the i's, and every element here is a linear combination of x to the j's, and this map here is a linear. I can only focus, I'm allowed to focus only on x to power I comma 0 and 0 comma x to power j, and try to see where they are going and write them in terms of an A-linear combination of powers of x. So that way I can list the coefficients and end up getting a matrix that tells us how this A-linear homomorphism work, this A-module homomorphism work. So this is an A-module homomorphism, and I want to represent it using a matrix. And again, because I need the same number of variables that I start with and I end up getting a square matrix. And what is this square matrix? I give you a polynomial f with the coefficients f sub i's, and I give you a polynomial g with coefficients g sub i's. Now I multiply, let's say I take something over here, x to the power I, comma 0, and I ask myself, where does it go? It goes to x to the power I times f plus 0. So I need to understand what is x to the power I times f. But x to the power I times f is just shift of f. So I'm shifting all the coefficients of f I steps. Now if I plug in 0 here and x to the power j here, I end up getting x to the power j times g. And x to the power g times j times g is shift of coefficients of g, j steps. So if I write them in this way, in the unique way that we can, in p sub d plus m minus 1, the coefficients, if I write them the usual way that we do it in linear algebra, put it in the columns of this matrix, I end up getting this matrix. So coefficients of f, then I need to shift it by 1, then by 2, then by 3. And how many steps, how many shifts should I go? I need to start with 0 shifts till m minus 1 shifts. So that means I get m columns out of this that are shifts of f. These are essentially coming from x to the power I times f, where I ranges from 0 to till m minus 1. Then I need to shift g. And that means that first I write down coefficients of g, and then I start shifting them. And then I shift them from 0 shift over here till d minus 1 shifts over here. Now notice that here, this block, I have d of these, and then I have m of these, sorry. I have m of these. So this means that I have m columns over here, but the next one, I have m plus 1 over here. So this means this is at the position m plus 1, m plus 1. This means that the diagonal of this matrix, we understand. All these elements are on the diagonal of this matrix. I have m f sub 0 is on the diagonal, and then d g sub m's in the bottom part of this diagonal. So we start with the constant term of f, m times, and then the leading coefficient of g, d times. Okay, so this is a matrix representation of this linear map. And this matrix representation, if I understand this matrix well, then I can understand this map well, which in turn can tell me what are the polynomials that can be written as a linear combination of f and g. But we are going to use this in an interesting way. So what do I mean by that? So let's observe that when I multiply this matrix from left by the row matrix consisting of powers of x, let's see what we end up getting. When I multiply this row by this column, I get 1 times f0 plus x times f1, x squared times f2, x to the d times fd. That's precisely f. So that means that the first component of this product is just f. Then when I multiply the same thing by the second column, I get a shift of it. It's x times f. Then I multiply it by the third column, I get shift of it, and so on. So we end up getting that it is the first m components are f, x squared f, dot, x to the power n minus 1 f. Now, when I multiply it by these things, similarly, we end up getting g, x times g, dot, and we get the last one is x to the power d minus 1 times g. So by multiplying this row matrix by this square matrix, capital R of f comma g, we end up getting f x f dot x to power n minus 1f g times g x g dot x to power d minus 1g. We have seen the importance of the adjoint matrix and determinant, so let's multiply both sides by the adjoint of this matrix and see what we end up getting. When I multiply both sides of this equation by the adjoint of this matrix, we end up getting by multiplying by this adjoint matrix, we end up getting determinant of this. Now it's a scalar matrix, so it doesn't matter if I put it on the left or right. Now I'm just scaling it. It's determinant of this matrix times this row matrix, and that's supposed to be, you see, here I have all these elements are multiples of f, and all these elements are multiples of g. When I multiply it, when I multiply by the adjoint of this matrix, all the entries would belong to the ideal generated by f and g. That means that when I multiply by the adjoint, I definitely get a row matrix consisting of entries in the ideal generated by f and g. In particular, the first entry is in the ideal generated by f and g. The first entry is determinant of this matrix. Determinant of this particular matrix is called the resultant of the polynomials f and g, and we are going to denote it by small r of f comma g. And what we have proved is the following, that if f and g are two non-constant polynomials in a bracket x, then the resultant of f and g is in the ideal generated by f and g and in the ring of the constant, the ring of coefficients. So again, we were looking for such a thing. We were looking for a mechanism to find elements in the ideal generated by f and g and be constant. And using this determinant in a twisted way, we end up finding such an element. In certain cases, this element might be just 0, but nevertheless, this is a general mechanism that can give us an element inside A and the ideal generated by f and g. So let's actually make sure we know why this is the case. By this argument that we have over here, the first entry, which is this resultant, should belong to the ideal generated by f and g. So that means that the resultant is inside the ideal generated by f and g. But at the same time, we know the resultant is determinant of this matrix with entries inside the ring A. Because it's in the ring A, determinant of this matrix belongs to the ring A. So the resultant is inside the ring A. So it is both inside the ring A and in the ideal generated by f and g. Okay, so not bad. We wanted to find a method of finding elements inside the constant polynomials and the ideal generated by f and g, and we managed to do it for an arbitrary unital commutative ring. Now let's see how this can help us. Let's recall that using this contrary assumption that pi is not surjective, using the contrary assumption, where was it? Using this assumption that pi from z of I to common zeros of I to common zeros of I intersection with one less variable, assuming that this is not surjective, we end up finding a polynomial f with these properties, that if this polynomial is given like this, and when I evaluate the coefficients, all the coefficients except the constant one are going to go to 0. The constant one is going to go to 1. That is what we showed. So let's write down this star prime. So let's assume that A is a common zero of the polynomials inside I with one less variable. And let's assume that I have a polynomial f inside I, so that all the coefficients, when I evaluate all the coefficients except the constant one, I end up getting 0. When I evaluate it at this common 0, I get 0. And the constant one is evaluated at A is 1. So that's our assumption. That essentially comes from the bad position. When pi is not surjective, we end up getting this star prime. Now let's see what we can get out of it. By this lemma, I know, by this lemma over here, I know that for every g inside the ideal I, the resultant of f and g, f is this one, f is also inside I. We know that because g and I, f, both of them are inside I can use this. The ideal generated by f and g would be still inside I. So by that, we get that the resultant is still inside I, and it is inside A, which means it is inside the ring of polynomials with one less variable. So the resultant is also inside this ideal. It is inside I and polynomials with no variable x sub n, which means A bar is a 0 of the resultant, which means when I evaluate the resultant at A bar, I end up getting 0 for every g inside the ideal I. Okay, let's see. What does resultant mean? Let's recall. Resultant is determinant of certain matrix. I'm going to write it again. This matrix comes from coefficients of f shifted degree of g times. So written degree of g times, but each time shifted one down, and then coefficients of g written degree of f times. So each time shifted one step down. So that's my matrix capital R of f and g, and now I need to evaluate these polynomials at A. Now think about it. When I evaluate it, what happens to this matrix? I'm going to write it down, but here is a claim. Remember, this f has this property that when I evaluate it, many of the coefficients end up being 0 except the constant one. That means that when I shift these values of, I start with the coefficients of f and I shift them down, so except the constant one, which is on the diagonal, the rest are 0. So all of a sudden, I end up getting an upper triangular matrix. I will write it down and you will see it is written in the next page. I end up getting an upper triangular matrix with diagonal entries equal to, okay, let's actually take a look at it and make sure that we understand it. See, f sub 0 is 1, f sub 0 is 1, f sub 0 is 1, but the other terms are all 0. So all these terms are 0. As I have mentioned, on the diagonal we have these. Essentially the constant term of f and the leading coefficient of g, both evaluated at A. So as we can see here, this is my diagonal. All the things, all the entries below the diagonal are 0. So we end up getting an upper triangular matrix with diagonal entries equal to m of them are 1 and d of them are g of m evaluated at A. That means determinant of this matrix is the leading coefficient of g evaluated at A raised to power d. So that's the resultant of f and g evaluated at A. Now, by our assumption, remember A is a common 0 of I intersection with ring of polynomials with variables x1 x sub n minus 1, and resultant belongs to this ideal. So we know that resultant evaluated at A is 0, and by this matrix we have computed the resultant and we realized resultant is the leading coefficient of g evaluated a raised to power d. This is supposed to be 0. That means for every g that you give me inside the ideal, the leading coefficient of g evaluated at a should be 0. That's quite interesting. Let's summarize what we have proved. We have proved that if pi failed to be surjective, well, what is pi? Pi is the map from the common zeros of I to common zeros of I intersected with one less variable. So that's projection from this common zeros to these ones. So I'm essentially dropping the last component. If this pi fails to be surjective, so to be concrete, so suppose A is a common zero of this intersected ideal, and there is nothing that has these first n-1 components in the common zeros of I. So suppose it's not surjective, this vector A does not belong to the image of pi. If this is the case, then we proved that for every g that you give me inside the ideal, the leading coefficient evaluated at A should be 0. This is what we proved out of using the resultant and the function that is evaluated and end up giving us the constant function 1. So altogether, we end up getting this interesting result that if pi fails to be surjective, then for every g inside the ideal I, the leading coefficient evaluated at this A that fails to have a preimage should be 0. Okay, so this means, in particular, it means I cannot find a polynomial inside I whose leading coefficient is a constant, non-zero constant coefficient. I cannot find a monic polynomial here. I cannot find a non-zero constant polynomial inside I. That's a particular case because all of them should have a 0. So they cannot be constant non-zero polynomials. What we will do is to change coordinates in a linear way and then make sure that in this new system of system of coordinates, and actually there is some g that has non-constant that has constant non-zero coefficient as its leading term, and therefore in this new system of linear coordinate system, pi is indeed surjective. So that's our goal. This is how we are going to get surjectivity and get some element inside z of I. So again, our goal is to find a linear change of coordinates that allows us to find an element g inside I, where g sub m, the leading coefficient, is a non-zero constant polynomial. This clearly contradicts this lemma, because this lemma tells me that contradicts unless pi is surjective. So if pi is not surjective, this lemma tells me that there should, whenever pi fails to surject onto a vector A, then the leading coefficient evaluated at A should be 0. In particular, this cannot be a constant non-zero polynomial. If I manage to find such a GM inside I, that would imply that pi is surjective in this new linear coordinate system. So after making this linear change of coordinates, pi ends up being surjective. Okay, so how can I make sure that I have such change of linear such linear coordinate system? Remember that F is algebraically closed. In particular, it cannot be a finite field. We know that every finite field, if it has p to the n elements, then a polynomial that has so x to power p to power m minus x, where m is more than n, does not split into linear factors. A finite field is not algebraically closed. So every algebraically closed field is an infinite field. Now, in this lemma, we can in fact relax and write this lemma only for infinite fields. So suppose that F is an infinite field. Now I'm going to produce automorphisms of ring of polynomials in n variables that are essentially coming from linear maps. So I'm going to change the coordinate system of f to the n from x sub i's to some linear change of x sub i's, and then plug in into the polynomial f. Okay, let's make it concrete. So suppose I've given you this infinite field, and I've given you this polynomial h that's not constant. Now, first I'm going to introduce a certain family of automorphisms of ring of polynomials. So what are those? For a given set of coefficients, alpha i's, inside f, so it's like a vector inside f to the n minus 1, I'm going to define theta of this vector from the ring of polynomials to itself. Now, how does it work? First, I make this linear change to the coordinate system, xi's, and I send x1 dot xn to these coordinates, x1 minus alpha 1 x sub n, x2 minus alpha 2 x sub n, x1, here I should write it as x sub n minus 1, x sub n minus 1 minus alpha sub n minus 1 times x sub n, and I'm not changing the last one. So it's kind of a reduced row process here. I'm multiplying the last column by different scalars and subtracting the first one, the second one, and so on. After that, I'm evaluating f in this new value coordinates. So, and then I consider f of this new coordinates. I call this to be theta sub alpha of f. My claim is that this is an f isomorphism from the ring of polynomials in n variables to itself. So it's a ring homomorphism, it's bijection, and so on. Now, the second claim is that I can always find some vector so that when I apply theta sub a to this h that you have given me, this non-constant polynomial that you've given me, I end up getting a polynomial with non-zero constant leading coefficient. So I can always find some a so that when I apply this isomorphism to h, I end up getting a polynomial that has non-zero constant coefficient in terms of x sub n. So if I view this polynomial as a polynomial of x sub n, I end up getting a constant non-zero leading coefficient. So that's going to be our source of finding something inside I that is not, that has no, that has a non-constant, that has a constant non-zero leading coefficient. Okay, so let's see how the proof goes. The main observation is what I've already mentioned, that essentially I'm applying these linear actions to x sub i's and then composing them with evaluation map. So in particular, okay, let's look at the composite of two of such thetas with two different vectors. So suppose I give you two vectors a and b in f to power n minus 1, then apply these thetas one after another, one with parameters b, the other one with parameters a. See what happens to the polynomial f. When I apply this one to the function theta b of f, it means that this polynomial should be evaluated at the point x1 minus a1 of xn, x2 minus a2 of xn, x sub n minus 1 minus a sub n minus 1 of xn, and the last coordinate doesn't change. Now, when I apply this theta of b to f, and I want to evaluate it here, what does that mean? This means whatever variables, whatever components you give me, I have to subtract bi multiples of the last one from the ith component and then plug it in to f. So this means I need to evaluate f at the first coordinate of this minus b1 times the last coordinate. The second one minus b2 times the last one. The n minus 1 term minus b sub n minus 1 times the last term. And the last term doesn't change. So altogether, we end up getting this. But this is what? This is a1 plus b1 times the last term. a2 plus b2 times the last term. So this is precisely theta sub a plus b of f. So it is a map of the same type, but the parameters add up. In particular, if I compose theta sub a to theta sub m negative a, or if I compose theta sub negative a with theta sub a, in both cases I get theta sub 0, which means identity map. That means both of these are inverse of each other, and so this is a bijection. Now, the fact that this is a ring homomorphism, an F-linear ring homomorphism, is rather easy. Again, the whole point is that it's a combination of this linear change of components and evaluation. And because of the fact that it's essentially, at the end of the day, an evaluation map, gives us the fact that it is indeed a ring homomorphism, and it's an F-linear map as well. So I leave that part for you guys to check. And again, it is important to notice that theta of a of f is essentially evaluating f at this. So I'm applying this upper triangular matrix to x1 dot xn and then plug it in to f. This is another hidden relation with the reduced row column process. Now, let's see what happens as I apply this theta of a. Now, theta of a, we know, is a ring isomorphism. And every element in this ring of polynomials can be written as an F-linear combination of monomials. So in order to understand what theta of a does to a polynomial, it's enough to understand what it does to monomials. If we understand good enough what it does to monomials, then we can understand and describe what theta of a does to an arbitrary polynomial. Now, suppose I give you a monomial, and that means that I'm giving you, so I'm ignoring the coefficient, I'm just thinking about monomials with coefficient 1. That means I'm giving you some non-negative integer power of x1, some non-negative integer power of x2, and so on. So I sub i's are non-negative integer powers. And the total degree of such a monomial is defined to be summation of these I sub i's. Okay, so now it's a good stop. It's a good place to stop the proof. In the next lecture, we continue with the second part of this, this argument. So far, we have proved an important lemma that if pi fails to be surjective, then the leading coefficient of G sub n's evaluated at this common 0 should always be 0. Now we are using this process and using these theta sub i's, theta sub a's, in order to produce an element of the of some ideal with a constant non-zero leading coefficient. So we will continue with the proof of the part B of this lemma in the next